Here it is, timeouts. There. I can make it stay awake now.
Oh, so we can share it.
Okay.
Are you looking for something?
Yeah.
So after you do the chair slides, then she does three presentations in a row.
So it's okay. Time fast.
Oh, yes, it is.
Time to start, please. Start the mic. Just grab the whole stand.
Good afternoon, good evening, everyone.
Leaning from microphone, it's hard.
Okay, yes, much better. Now I can hear myself. Good afternoon, good evening, everyone. My name is Ron Bonica. I'm the new chair in the party. You know Asian, you know Joel. Sorry. We'll start out with the note well. It's Thursday of IETF week. You've all seen it many times before this week, but I would recommend everybody take a look at it because it does have important stuff that you probably overlook for many IETFs. The status of the working group, we've adopted six internet drafts. The intra-domain document, the intra-domain problem statement, the inter-domain problem statement, intra-domain architecture, capabilities, and bar SAV. We also have many other many other documents that haven't made it into the working group yet that aren't listed here, but interesting to look at. The goals of this meeting. Number one goal is the intra-domain SAVNET PS document. We want to revisit that. We want to get it in good enough shape to send it back to the AD. Second goal is the inter-domain solutions, and third, management. And you'll see we have a quite full agenda. So I would ask everybody to be very mindful of time so the next presenter will like you. You'll see at the bottom of the screen, there's a little timer. Do pay attention to that. You see a very full agenda, and I'm not going to run through every draft we're going to touch. And I will call the first presenter, who I believe is
You're
Yeah.
switching the slides and
I
you
see.
come up while we're doing it.
Here you go.
Thanks.
go, and that click
You
button
can.
now has, you have control of the slides.
Oh, he doesn't have the timer.
Oh, I can find the time.
Okay, hello everyone. I'm Lan Cheng from Zhongguancun Lab. Today I'm going to introduce the recent progress of this document. Since IETF 123, there has been a lot of discussions on the mailing list related to this document, including whether to split this document into two documents, one for problem statement and then the other for requirements, or discussions on the intra-domain self-deployment locations, the definition and the wording suggestions for intra-domain subnetworks, and on which document should handle non-BGP customers, the intra-domain document or the inter-domain document, as well as on the definition of intra-domain hidden prefixes. For the first discussion, the working group consensus is not splitting this document into two documents. And we must clarify in this document that these informational requirements cannot be used to initiate standards track protocol changes. And for the second discussion, the clear conclusion is that the working group chooses to focus only on edge documents, or in other words, serve at external interfaces. And serve at internal interfaces is currently out of the scope. The authors also clarify the definition of intra-domain subnetwork. Actually, the term is intended to refer to a non-BGP customer. The idea is to capture scenarios when the custom network doesn't run BGP with the operator, and SAV is applied at the boundary between the operator and such a non-BGP customer. We also solicit wording suggestions for this term. And according to mailing list discussion, we finally choose to replace this term subnetwork with non-BGP customer network. And as for the discussions on which document handle non-BGP customer, the final decision is that it's intra-domain because it requires information that doesn't come from BGP. The authors clarify the definition of intra-domain hidden prefixes. Specifically, it refers to a host that sources traffic with a source address not allocated by the operator, or a non-BGP customer that sources traffic with an address not advertised to the operators. In this case, the key challenge here is how to provide authoritative information to authorize the host or the non-BGP customer to use such source address. So based on working group consensus and working group discussions, we made the following main updates, including clarified that this document currently focuses on intra-domain self-deployment at external interfaces, and replaced the term subnetwork with non-BGP customer, and clarifies definition. We also refined the description of the intra-domain hidden prefix scenario, and add a new discussion section on the potential for incorrect routing information, and make the clarification in requirement section that these requirements should not be or cannot be used to initiate standards track protocol changes. We also clarify and distinguish the incremental deployment and incremental benefits in the requirement section. And we also remove references that were not cited in the document and correct some wording issues according to the Schaeffer's review. We thank our Shepherd who carefully reviewed these documents, and she is fine with these updates. And we also thank our chairs to issue the open discussions and announce the working group consensus and move this document forward. So next, we think this document is almost ready for reissuing the working group last call. And that's all. Thanks.
Thank you very much. And I do see one person in the queue. Julian?
Thank you, Chairs. It's Jian from ZTE. I take the shepherd of this draft. So first, I would like to thank the authors to, you have made hard work on addressing comments from the IESG and a working group. I believe that the working group has conducted a wide discussion on problem scenarios and a definition and requirements. I think the current draft can reflect the consensus from the working group. And I also think it's clear to me. So I would like to express my support of this draft to progress it to the second WG last call. Okay, thank you.
Thanks.
Thank you. And one more person in the queue, Shengan.
Oh, hi, it's Shunan from China Mobile here. And I also think this draft has been fully discussed, and the scenarios and problems seems reasonable to me. So I think it's ready to working group last call, and I hope we can put that forward. Thank you.
Yeah, thanks for the comment.
Okay. And
Who's the next presenter as well?
Yeah.
So we need to-
do we need,
There is a second, he will present the second text presentation.
Oh, okay. Okay, the intra-domain SAVNET architecture. Yeah, as mentioned earlier, there has been a lot of discussions related to the intra-domain self problem statement, and some of those discussions are also related to the intra-domain self architecture. For example, there has been some discussions on deploying self at internal interfaces. Somebody believe it can help to mitigate source address spoofing by compromised intra-domain routers. But most participants believe the problems caused by compromised routers are beyond the scope or are even beyond the charter. So we think we should focus on the self at external interfaces, and also a discussion related to the intra-domain self deployment locations. And we finally make the clear working group rough consensus. So according to these discussions, we revised the intra-domain self architecture document. Specifically, we first add a new section 3, the threat model, which clearly defines the threat model of intra-domain source address spoofing. And we also add a new section 4 to describe the deployment scope of intra-domain self and presents the representative use cases. So in the new section 3, for the attacker, we think it can be a directly connect host or a non-BGP custom network or an external AS for an intra-domain network. And the attackers can inject data packets with spoofed source addresses into the domain, specifically at external interfaces facing a host or facing a non-BGP custom network. Attackers may attempt to send data packets with source addresses they are not authorized to use, such like using a source address of another network. And at external interfaces facing external ASs, the attackers may attempt to send data packets using internal use-only source addresses. So the intra-domain SAVNet should prevent these attacks. And we also make the following assumptions. First, we assume intra-domain routers are trusted and operate correctly. And spoofing traffic originating from a compromised intra-domain router is out of scope. And then in section 4, we clearly define the deployment scope, that is, serve at external interfaces. And we describe the two use cases. The first one is intra-domain SAVNet at external interfaces facing host or non-BGP custom networks to prevent them from injecting source address spoofing traffic using a non-authorized source address. And the second use case is serve at external interfaces facing external AS to prevent them from injecting data packets with internal use-only source addresses. Yeah, thanks everyone. Any comments?
The queue seems to be empty.
OK， thank you。
Next is also mine.
Next question is update for the capability. 黄，你是黄呀？你去。
Hang on just a second.
Okay.
OK。
Hello, everyone. This is Minqing Huang from Zhongguancun Laboratory. I'm going to give closer. Okay, much better. This is Minqing Huang from Zhongguancun Laboratory. I'm going to give a very quick update on general SAS address validation capabilities. Actually, this version is version 03, and just one update based on the feedback from Jeff at the last meeting. Thanks for Jeff that the problems he mentioned is that right now, before that, the SAF mode naming we use a number, but that is not maybe it's not proper because number itself has low semantics and also may related to number assignment. So in this version, we changed the naming to abbreviation-based naming system that which listed here. So, for example, the IBASAF stand for interface-based preface allow list, and IBBSAF stand for interface-based prefix block list, etc. I'm not going to go to details. That's the many updates on this version. And also because according to the recent discussion, I have more open issue for this draft. So we may want request for working group last call. Thank you.
And the queue is empty.
I think this document is stable and we will consider it for WG last call. Yeah, okay. You can print. Yeah,
Go ahead.
go ahead.
Okay.
We'll come back to the one we skipped.
Yeah, I was expecting something before. Okay, sorry about that. Hi, I'm Amir Herzberg from Yukon, and I'll talk about our simulations of routing reverse path forwarding SAV methods, URPF and BarSave. Okay, that's joint work with Nick Scaglione, Justin Furness, Yossi Gilad, Chemi Leibovich, Cameron Morris, Bing Wang, and Sriram Kotikalupudi. Okay, so doesn't. Should it move?
Yeah, I see you can. I have, oh, here. Hey, oh.
Now?
sorry.
Oh. Yes, good. Okay, so our goal was to do realistic and comprehensive simulations of reverse path forwarding methods. So methods which are not involving any new protocol, but using just building reverse path forwarding, using existing other resources, right? To evaluate them in a realistic as we can, using the internet AS topology, which we take from CADA, and relationships, estimation, of course, taken from CADA, measuring both the false positive rates and the detection rates, or the true positive rates, evaluate the performance under partial adoption rates, different partial adoption rates, as you will see, and including to measure the impact of traffic engineering methods, which is a significant impact, as you can expect, of course, but this required us to have some measurements of that. So we did some simple measurements of traffic engineering methods in use in order to make a realistic or a more realistic measurement of the impact of different reverse path forwarding methods. Okay. Now the policies we've evaluated, and some results will not be in this presentation, of course, but only in the paper. If anybody interested, ask me. I can send you the current draft of the paper. So we've evaluated strict URPF, feasible path URPF, enhanced feasible path URPF. Both there are two variants, A and B, so we evaluated both of them. And BarSave, with and without the provider interface optional mechanism. Okay, so about traffic engineering and export policies. We've evaluated several, and we measured and then evaluated several. Of course, we've evaluated the classical export to all, which is a very commonly used simplification. In fact, I think that in all the works we have seen, this was in all simulation works of different, BGP security works. I think that universally everybody just used the simplified model of export to all. Although everybody, maybe not everybody, but everybody, most people working in this area are well aware that not every AS is exporting every prefix to all of its provider, what we call export to all, right? So that we did evaluate under this simplified model. We also evaluated, measured and then evaluated ASs doing path prepending, a very widely used technique for basic traffic engineering. And we also evaluate some more, I would say, more aggressive methods of traffic engineering, specifically partial export to some, where some prefixes are exported only to some of your providers, or they may be exported also to other providers, but with the no export community. So it's almost the same as exporting only to some of your providers, not exactly, of course. And also, we evaluated an even more aggressive case and more extreme case of no export to some, which means that to some of your providers, you simply don't export any prefixes. Now, that can seem weird. I mean, why do you have a provider if you don't export anything to that provider? However, from what we understand, this is actually a scenario which is used. I've also seen some messages in Nanog about it and so on. Seems to be, and also we did a survey of operators, and again we learned that some people say that they use this method. So
this appears to be much in use. Now you notice that I put all of these disclaimers, and I said that we did measurements. So why do I put these disclaimers if we did a measurement of different traffic engineering? Well, the problem is that if you don't export anything, and our measurements are of course relying on what you get from the collectors, on the BGP announcements from the collectors. Now, if you don't export anything, you will not see this in the collectors, right? So, and also it may not even appear in CADA. It's actually likely not to appear in the topology of CADA because they will not see it. I mean, they are building the topologies based on what you get from the collectors. So these kind of situations, we clearly have under measurement. It is a challenge, an outstanding challenge, and I have some friends here from the academia. So guys, this is an outstanding challenge for all of us in the community to actually find a reasonable way to do it. I have some ideas. We can discuss it later if anybody is interested, but this would be a challenge for sure. This will require much harder, I think feasible, but harder measurements. So we didn't do it. I mean, how do we don't do, right? So we also evaluated, did a simulation for the situation of direct server return, where we use some prefix to send, but we don't export it. We don't export this prefix at all to any of our providers, right? So we also evaluated that situation, which is mentioned in the bar save draft. Okay, so how did we measure the traffic engineering? So don't expect too much. As I said, this was not our focus, but we did need to have some measurement of traffic engineering. So we did a basic one. Hopefully in the future, we'll extend it to a more extensive one, or some of our colleagues will do that. And then we can get even more, refined results. So again, we use the CADA AS level topology with in public routing information from RIPE and route views, the collectors. We do note that there is this underrepresentation of no export to some, these scenarios where an AS just doesn't export anything because this will not be visible. And then we measured only for edge ASs, and in fact, I wrote here edge ASs, but this is actually not precise. We measured only for multi-homed edge ASs. The reason we didn't measure for stubs is because stubs are kind of have a single provider, so they are a non-interesting case, non-interesting case here. But the reason we didn't measure for transit AS is because we need to, this is a more difficult computationally measurement. Again, we are actually working on doing that right now. It is feasible. We are doing it, working on that right now, but we didn't do it in this initial study. Okay, so focusing on the multi-home DSs, okay? So this is what we found, okay? We found about half of them are doing export to all, and you see that these diagonal bars represent the ones which are doing some path prepending, and the one without the diagonal bars are without the path prepending. So about half are doing path prepending, half don't do path prepending, roughly, right? And about half doing export to all, and half doing partial export to some. Again, we have a very small number of measured no export to some, but we are quite sure this is underrepresentative because these are just the ones that CADA did identify, maybe from some earlier, measurement, but most of them probably you just don't have in CADA. Okay, so the methodologies that we used. So we developed, not for this research, already a few years back, and we used it in multiple research about secure inter-domain routing, a simulator specifically for secure inter-domain routing scenarios, which is called BGPy. It's called BGPy because it was developed in Python, right? Although we are now working, making a version, more efficient version also in Rust. And this is a open source. We use it in several works. Some other groups already use it in several works. So it's a nice tool. Everybody's welcome to use it. And we extended it for this research, first of all, of course, by implementing the different source address validation policies, and also to do the data plane traceback. I mean, we did have traceback before, but now we're doing it in a data plane and not in the control plane because this is critical in this scenario. And also to add the relevant performance metric tracking, which we need for this research, which are a bit different from, source prefix hijack and so on, the source inter-domain routing problems. We integrated the traffic engineering measurements into our routing models, and it's open source, so it's also available online. Again, we model the internet based on CADA, the ASS. There may be some relationship in CADA, of course, that are missing or incorrect, which could lead to some inaccuracies, but most significantly to scenarios where there is a disconnection. If there is a disconnection, you could get a wrong result, like a false positive or a false negative, which will mislead you. So we actually have removed any scenario in which we get, we don't have connectivity. So we will not think that there is a false positive just because there is no connectivity, because there's some missing information in the topology, right? Which has nothing to do with source address validation. So we remove these scenarios, okay? Yes, and we only model, basically CADA only models this customer-provider relationship and peer-to-peer relationship. We don't have enough data on the more complex, relationship, siblings, and so on. And we use random edge multi-home ASs as both the legitimate origin and the spoofer. We measured all of these scenarios that I mentioned already. I will not repeat the names. With varying percentage of adoption, as you'll see in the graphs. We measured 2 attacker models, because for source address validation, you really should consider these 2 models. I think this is actually an important point for everybody to take home. Because that's something that at least we didn't think about initially, but we do have 2 different attacker models possible here. One where we have a spoofing host. So the routing used by the packet is the regular BGP routing between, right? So, but the alternative is when the AS itself is involved in the spoofing, in which case the AS could send, not according to BGP routing, it would send to some neighbors that by BGP routing it shouldn't send, right? It may increase its chances of doing successful spoofing. So we compared both of these, and we had 1,000 tiles, 5 destinations each time, and you'll see the error bars for 95% confidence intervals. Okay, so here are some of the results. Export to all, simplified model, obviously not completely true, but kind of idealized routing scenario. And not surprisingly, in this case, most of the policies actually avoid false positives. So it's great, right? And you can see in the, there is a pointer, but it will not work, right? Pointer, does the pointer work for?
Oh, no.
No, it doesn't.
They can't see it.
They can't see, okay. I can point here. Okay, so if you can point, so at least you guys can see it. Okay, so I'll use it here.
But the people online can't see it.
Well, but at least something, right?
Yeah.
I mean, also talk. So I mean, right. So as you can see on the right-hand side, we see the detection rates, right? On the left-hand side, we see the false positive. Let's first look at the false positive, because this is a big, big problem of source address validation, right? The big stumbling block for deployment, or one of the big stumbling blocks for deployment, there is another one, which is, of course, incentive and motivation. But one of the big stumbling blocks is obviously the fear from false positive. By the way, in our survey of operators, we also confirmed this intuition. And yes, that's what people are most concerned about. Okay. So false positive rates you see is that strict URPF obviously has a lot of false positive, but all the other policies have basically none, or actually none, except for feasible pass, which has a bit. This bit is a bit compared to strict URPF. This bit is still over 1% if in full adoption, so it could be a problem definitely, right? In early adoption, in low adoption percentages, it's very, very low. Okay, and we are talking here about using it only for customers and peers, because that's what in the standard we have compared these 2 scenarios, right? The standard does not allows the 2 options of applying to customers and peers and applying only to customers. If you apply only to customers, you will have the no false positive. So in this nice scenario, yes, feasible pass. I mean, if reality was so ideal, we could have used feasible pass. Yes, and life would have been simple. But I guess life is not. Now turning to the figure on the right, the detection rates, here we see that strict URPF is actually doing pretty well. I mean, relatively speaking, because actually, and this may be another important point to take home, even if we do strict, you see, and even if we are in export to all and everything, we would still have detection rate only really good only when we have adoption really good, which is not realistic. If you look at lower adoption rates, we will actually have limited, but still useful detection rates. Okay, so basically this should motivate us to have additional solutions. I'm not saying we shouldn't use this sub-mechanism, we should, but we probably should consider having additional defense mechanisms. Okay, and you see all the other schemes have lower detection rates, right? Where some of the best schemes, which are relatively close to strict, are BarSave and EFPA, EFPBA and EFPB, and feasible pass, right? Okay. So that's what I actually wrote here, that BarSave and EFPA with bilateral peers in BarSave with provider interfaces have good detection rates and no false positive. But I say again, no false positive only in this default assumption, right? On this simplified export to all policy. Let's look what happens with more realistic policies. Okay, so first let's look at our measurement. So this is when we use the traffic engineering, the way we measured it. So for an AS in the simulations here, we just use for every AS, again, every multi-homed edge AS, we use the traffic engineering that we have found. Okay, what do we find this time? Okay, first we are focusing, let's actually first focus on the two smaller figures on the top. The two which show the false positive rates on the left, and here we see that basically all of this, very similar to what we had before, right? That strict is terrible, and now we have feasible pass, but now feasible pass is really quite bad, right? Not like before, which it was pretty low percent. Here we are getting to really very significant percentage, truly unacceptable for false positives. But the rest seem all to be zero. But let's go now to the figure below where we zoom in, because false positives are a big problem, right? So we want to zoom in and to see the results for false positive, more precisely. And here we see that only one policy is strictly zero, which is BarSave with provider interfaces. This is the only policy which is strictly zero, okay? And that is only under the assumption that the origin has ASPA. Only if the origin has ASPA, we get this, okay? Now, if the origin does not have ASPA, then BarSave is comparable to EFPBB, basically. EFPB and also EFPBA. EFPBA is actually even slightly worse here, it seems. Of course, we do have confidence intervals, and since these are talking very low percentages, you should not be surprised that the confidence intervals are mostly quite large, right? So we probably need to do many, many more runs in order to get them smaller, but the basic results we think is unlikely to change. Okay, so now look at the scenario of no export to some. So again, since we couldn't do this based on our measurements, because our measurements are clearly terribly under measuring these ASs, so here we use some just time.
You're very close.
Oh, 2 minutes. Okay, good to know. I'm not that bad, I think. I'll just rush a bit more. So basically, the results show that with ASPA, BarSave has no false positive like before, while maintaining high detection rate. The detection rate on the right here, you see, BarSave where is BarSave? BarSave, I lost it. Okay, BarSave is right here, you see, so it's almost like strict, right? So it will have very high relative, again, detection rate, while false positive still on the zero. That's the most important result. I guess I can skip the rest because we are running out of time. Direct server return. Direct server return, this very important scenario in which we have a prefix which is not announced at all to any of your providers, right? And as discussed in the BarSave RFC and on the list and by many people, it is actually a very existing scenario. So again, we see that BarSave is doing fine, right? No false positive. However, obviously, this is assuming ROAS, right? Or TOAS. I mean, if you adopt BarSave and use TOAS instead of ROAS, I think from this point of view, it's basically equivalent. You mean you're doing a ROA without announcing, so it's basically the same as doing a TOR, right? Okay, so that's what we get. And key takeaways from this: traffic engineering has significant impact on the SAV results, right? We definitely have more false positives, even a bit for bar save in some, in specific scenarios. Now, you may ask which scenarios. So, because it is seen that bar save has 0 all the time. Well, certainly, if you don't have a ROA for DSR or you don't have ASPA, then of course you will have some false positive, first of all, right, for bar save. But also, remember that I said that we didn't measure yet traffic engineering by other ASs except for transit ASs, really, I should say. We didn't measure it yet. We are measuring it, but for now, we've done simulation using it, right, just randomly, and then we do get false positive. I run out of time. I can show later, anybody interested, or send me email and send you the results. And we also have a nice example, but that was for if I run out of content and not out of time. And of course, this didn't happen. So again, anybody interested, I can show, I can send, whatever. Great. Thank you. Thank you very much. Sorry for being a bit out.
And no time for questions from this.
Right.
Thanks. Okay, Lan Cheng from Zhongguonceng Lab. I'm going to introduce an intra-domain SAV solution, which focuses on SAV at external interfaces. And here list the main updates compared to the last version. In section 3, we introduce a hidden prefix registration mechanism to address the intra-domain hidden prefix scenarios. And we also revise section 4, self-reward generation procedure, and add a new section 5 to provide our operational considerations for using this solution. This document provides 2 types of self-specific information. The first one is source entity identifier, SEI, which defines the source entity that originates traffic. A source entity can be either a non-BGP customer network or a host connect to the SAVNet router. And the SEI is a unique identifier assigned by the network operator to represent a source entity. And it can be also used to avoid improper blocking under a symmetric routing scenario, which has already been described in the last version. And this time I will introduce the other type of self-specific information is hidden prefix registration, HPR. It can provide authoritative information about hidden prefixes legitimately used by the source entity. And we believe the operator should maintain the HPR database, and source entity can register the hidden prefix they are legitimately to use for sourcing traffic in this database. But when a source entity wishes to register a hidden prefix, it must provide authorization proof that it is legitimately allowed to source traffic from that prefix. And one possible proof is a TOA, or like a ROA, signed by the prefix holder. And after that, SAVNet routers can query or periodically retrieve HPR data from the database. So we revised the self-reward generation procedures, and we encourage everyone to read the document and give us some feedback. So here I will just summarize the key idea here. And for self-at external interfaces facing a non-BGP customer or a set of hosts, the router should use both SEI and HPR self-specific information to identify the whole source prefixes that the connected non-BGP customer or the connected set of hosts can use to source traffic. And then it will construct the allow list, including this prefix at the interface. And for self-at external interfaces facing an external AS, it should first extract internal use prefix from the intra-domain routing protocol, and then it should filter out externally valid prefixes. It can learn this information from ROA or TOA signed by other prefix holders. And then it can get the remaining set of prefixes, which should be the internal use only prefix. And it will construct the block list by using this prefix. And here are our operational considerations for the HPR database. First, the operator maintains the HPR database, and it must record the hidden prefixes and their bounded SER of the source entity. And each source entity can register its hidden prefix or other legitimate prefixes in this database. And when they register the prefix, they must provide proof of authorizations. And each source entity must manage only its own data. And for considerations on synchronization with cell routers, we think routers must stay up to date to avoid improper blocking or improper permitting. And the consistency between routers is very important. And as for the SEI assignment and configuration, we believe for entities connected to multiple routers, all routers must use the same SEI at interfaces facing the same entity for correct prefix identification. So, but this is just a preliminary idea. So comments, suggestions, and cooperations is welcome. And
Peter Pshenak, Cisco. So I find this a bit complex to do what you want to do. Wouldn't it be much easier if you simply get those hidden prefixes as a part of your management plan and distribute this to the routers using the configuration to update statically or subnet rules instead of providing this live database? I don't believe these prefixes change very often, do they?
so your recommendation is to using configurations?
Yeah. I mean, how often does the hidden prefix appear and disappear?
So just configure the sub rule, or
Yeah.
But we want to make it a automatic tool.
Well,
So we think there is a database, and routers can automatically fetch data.
configuration database is also a database. I mean, you know where these prefixes are.
Yeah.
They don't come up and appear and disappear every other second. They are pretty much static.
Yeah, but in some cases, the operator may not know the hidden prefix used by the non-BGP customer.
Well, you better know.
Yeah, for example, the customer network may use a prefix belonging to another or assigned by another operator.
No, but you need that database registration would need to be something you trust, right?
Mm-hmm.
Anyway.
Yeah.
I mean, I just find
Yeah,
it's a bit more complicated than it needs to be. That's basically my comment. Thank you.
Yeah, thank you for your comments, and we'll think about it. Okay, thanks.
Hi, everyone. This is Minqing again. I'm going to present a very new solution for provider interface source address validation based on the customer corn source. Basically, this idea actually we discussed a lot in, I believe, in the early stage of this year. This related to the inter-domain problem statement. We have a lot of discussion whether we should do something on provider side of a custom core, and what we can do. So here's the background. I shared this two background in the mailing list. These two pages actually come from the slides I shared before in the mailing list. The first one is that about currently, provider interface side, we only have like loose URPF, right? So we actually, but we face more, threat from the outside of the internet compared to the customer side. Meanwhile, the tool is not good enough, right? The loose URPF. So here's the thing: what we can do to help on the provider interface. So the basic idea is that whether we can narrow down the allow list for the source progress on the provider interface. So basically, we have two categories of source block list generation scenarios. One is that for content current source. The other one is general remote source. So here, this document focuses on the custom current source. So the idea is that basically, because we know that normally the shortest path first. So normally the traffic between the customer host will stay within the custom core, right? So which means that we can block the source address coming in the customer through the provider interface. But yeah, this is a general idea, but there's some challenges because some customer may have alternative trusted link provider to connect to the outside internet. So there will be some kind of feasible detour path, right? What would be happen that this thing we need to figure out. So based on this kind of challenge, we provide two solution options. One is we call provide interface self for standalone custom core. The other one is for standalone plus custom core. So here's the details. What is a standalone custom core, which means that we need to subtract the sub custom core with the external transit link. So like we show here in the diagram that the left side, there's a alternative transit link. So the sub transit custom core should be subscribed from the whole custom core. And then we have a standalone custom core, which means they only share the transit link on the top SABR. So the top AS. So this is, in this case, the standalone custom, the traffic between them will now go through the provider interface side, based on the value-free policies. So to do that, we need to identify all these kind of alternative trust link without any omission, right? The other thing is, what if there's some source address with similar to source address in this custom core come from an outside network? Is there any case? This is two challenges we need to figure out. The first is how to construct a standalone custom core. The most important thing here, right, is that we need to, identify all the custom member AS. So the challenge is that sometimes we have hidden AS, which means we cannot, is visible in the CC top AS because, partial transit deployment. Partial transit means that the customer BGP message will only, be propagated to peer and a customer, other peer and a customer S, but not the transit S. In this case, this customer S or customer S group cannot be seen in the top S, right? So we have to do something to make it visible. So the idea is that we may need to pre-register a specific object, like partial deployment object, rather than waiting or ASPA objects deployment. Okay, this is the one thing. The other challenge we need to do with, after we collect all the source prefix for the standalone customer corn, right? It is visible in local reefs, right? But sometimes we have, legitimate source address come from outside network, especially for multiple origin ASs, which means same source prefix with the customer also, originated from outside the network. This is another AS, which means another AS can, issue the legitimate traffic with this specific traffic. So in this case, we also want to, explore all this kind of information that any prefix in the customer are related to MOAS, multi-origin AS. So this may relate on the RPKI roles, objects, or local management help. Okay, this is about the standalone customer. And what is standalone plus customer? So here's the idea. The purpose that if there's so many, alternative translink that may be standalone customer is forced more. So that means this block list is very short, is not meaningful. So sometimes and also we have the feasible detour path, but not always mean happen, right? Because this is not the shortest path. Actually, shortest path is always in the customer. So we can detect whether it really happened, the detour really happened. And also the other idea is that if we can get some collaboration mechanism between the customer AS, we can get this information automatically without additional help from the outbound registration. For example, is there any partial deployment or the customer member AS discovery and or the alternative translink discovery? We can do it automatically with the help between the AS. So this is the idea about standalone plus customer solution. It suggests that we need to set up kind of communication mechanism between the AS in the customer. So this is general procedures. We have two options. I'm not going into details for that. One is that I call it conservative mode. We start from the standalone customer and plus any any sub customer without detour happen. And aggressive mode requires all the AS in the customer support this kind of solution, and then we can subtract the detour subset. Okay, that's all solutions. So basically, this is quite a new solution, and I do think that we have challenges because from the provider side, interface side, it is quite open compared to the access side is more complex, but more challenging. But I mean, it's meaningful to do something because we are facing more threat from the outside network. So, this deployment. So, why deployment consideration is that we suggest the customer is the regional center. It's not kind of very high tier AS that across the region. That's not. We suggest deployment location. The other is for security. Just like I mentioned, the standalone plus we create the new communication mechanism. So we need to think about how to avoid 这个man in the middle attack, etc. Yeah. So again, this is for it's quite new. So any comments and to get more ideas are very welcome. And who have similar idea and interested in this area, welcome to join us. And also, as I mentioned, that we, for example, we may need to figure out how to address the challenge of the hidden AS. Is there possible to register partial deployment objects or any other way? And also how can we make the communication protocol works for the customer ASS? So anyway, it comes and collaboration are welcome. Thanks.
And we have two folks in the queue. Amir?
Hi. Okay, thank you for presentation. And I think that indeed having solutions which would work in provider interface is very important. Some small comments. First of all, you should remember that BarSafe does have some mechanism for provider interfaces. So you should, I think, also just mention it. The BarSafe does have something for, it's not a very effective one. So I don't think it changes much the motivation, but it does exist, right? BarSafe PI, right? Secondly, I want to caution that you should really consider also this traffic engineering that I was mentioning. So because of this traffic engineering, you may have some of these false positive, basically. So you need to watch for that very carefully. And I really recommend that you indeed do some kind of simulations in order to measure the impact of these techniques. I think it's very, very interesting. It's a big question if, if the levels of the ASS where you could apply this, the impact will be significant or not. It's actually hard to know before doing simulations. One last small comment / suggestion is you may want to consider identifying topologically the ASS that are appropriate for adoption of this technique, because like you said, it seems somewhere in the middle, maybe you can do it, right? You can identify them and then get good results for these ASS, and then maybe this technique could be useful for specific ASS you can identify kind of conditions. Thank you.
Thank you. Very good suggestion. I will think about it. Thank
you. Igor?
Yes. So first, so thank you for thinking about the provider interface problem. I was also going to mention that you need to look at BarSafe PI algorithm. It's quite similar to what you're looking at, you call standalone version. In practice, you did mention that you expect that shortest path will be the one followed. And while it's true most of the time, I mean, in practice, it's not always true. And avoiding improper blocks is, it's a critical thing to make sure, to ensure adoption. So that's just the comments I wanted to make.
Oh, I'm sorry, I'm not sure quite got your question.
No, there's no real question. It's just like a point. Make sure that you do look at BarSafe PI algorithm, because it is similar to your standalone algorithm in a way. And also in the real world, you will not. It's not always true that you will follow the shortest path, and it's important to identify those cases where the traffic might not follow the shortest path, and so you will receive traffic, let's say, from a peer and not from your customer not from a customer phone. So it's important for adoption.
Okay. So seems like we are talking about how to construct the standalone customer. Anyway, I will go offline to talk to connect with you. Okay, thank you.
Thank you very much.
Xue, you can begin and you can control the slide.
Okay, thank you. Okay. Xuan Song from ZTE. This draft is about PCP for source address validation, and this draft is from ZTE and China Mobile. Actually, we have presented this draft at last meeting, and PCE working group. So this time, we would like to request your feedbacks from the working group. When we talk about the, this draft is about to use PC solution to address source address validation. And when we talk about this solution, we would like to talk the challenges of the questions first. As we all know, the question is about the traditional methods such as ACL-based filtering and URPF method. For ACL-based method, as we all know, it should use a manual configuration, so it may bring up high operational overhead. And for the URPF, in the symmetrical scenario, there will be some questions such as false positive or false negatives. And this solution is about, we use PCE to address this question. And why is PCE? Because PCE can provide a centralized control architecture, and through integration of PCE with SAVNET, you can find this figure. The PCE can be acted as a controller, and this controller actually can be hierarchical, and the PCC is located in the underlay network, and in inter-domain AS scenario, the PCC nodes will be located in the ASBR. Through PCE mechanism, it can provide a centralized control framework and provide the global visibility of the whole network, and it can also provide the policy optimization and coordination of cross-domain. And about the procedure for PC to support the source address validation. First, it needs to collect the information from the underlay networks, and then generate the cell policies and compute the validation passes, and then deliver to the underlay network nodes. And through the policy deployment in the underlay network, it can export the status of the SAM. And what information will be carried, through PCEP extension? We will use the reference, the cell capabilities introduced in this draft. It will involve 4 modes for cell policies. And PCEP extensions, to support this information, a new TLV, which is related to self-specific information, will be brought up. And we propose to use open message to carry this information, and through the it also need to create a new object, this object to carry the specific information, and the detailed information will be carried in the object body. So we would like to request your feedback and comments, questions, and we will also keep updates of this draft, it will be progressed in PCE working group mainly. Okay, thank you.
Lan Cheng from Zhongguancun Lab. I'm not familiar with PCE, so I just wonder the use case of your solution. Is it used for intra-domain solve or inter-domain solve or both?
Yeah, okay, thank you, Lan Chen. I think this method, so first, the PCE is, it can acted as a controller. It provides a centralized controller architecture. And for this draft, actually, we mainly use PCE for interdomain because interdomain has some advantages such as, providing the global visibility of the whole network, for the cell policies. And it mainly can address the questions for cross-domain coordination of the cell policy. But this draft is not limited to the interdomain scenario. So yeah, I think it may be also to be used in intradomain. Okay,
Thanks.
thank you.
Hi, Xuan. Li Binliu from Zhongguancun Lab. Thanks for the work. I'm interested how this work so the meet the technical requirements proposed in the interdomain problem statement draft.
Okay. Thank you. Thank you for the question. I think the requirements raised in the in the problem statement draft, it may involve the dynamic rules update, and may also need to support incremental deployment for the PCE because it's a dynamic protocol. It can support dynamic cell policy updates. It can also be used for incremental deployments. Okay, thank you.
Okay, thank you.
Okay, now I'm going to introduce the updates on the tour. Let's have a quick review of tour. One of the key challenges in current solve mechanism is that the current system for validating the right to originate traffic with a given source address has been built almost entirely on top of mechanisms designed to validate the right to originate routes to that IP address. So if when the two align, this approach works, but it will create ambiguity and misalignment when they diverge. For example, in scenarios when traffic is unidirectional and there is no need to attract return traffic while route announcement, or where the return traffic is intentionally directed to another location, such as the DSR scenario, this approach will improperly block legitimate traffic. So, tour is a new APK-assigned object which provides a means of verifying the IP prefix holder has authorized an AS to originate traffic using a given prefix, even when that AS is not authorized to originate any BGP routes to that prefix. And during and after the last IETF meeting, tour attracted significant attention and inspired lively discussions on the mailing list. And we also talk about this design with Jeff, Job, and Antoine offline. And after that, Ego joins as a new co-author. After talking this document with some experts from SADROP's working group, they suggest us to first describe or discuss this document in SAVNET working group. And after that, when the document is adopted, the two working group can cooperate to move it forward. So we revise this document and submit it to SAVNET working group. And according to the discussions, we make the following updates. We further clarify the challenge and the use cases in section 1. We add a new section 6 to provide operational recommendations, and we add section 8 to summarize discussion results. In section 6, we believe a tour is primarily useful in scenarios when the traffic origin and the route origin differ. So when the same AS is both authorized to originate routes via an existing ROA and to originate traffic from a given prefix. In this case, if we still create a duplicated tour, it would add unnecessary storage and overhead in the RPKI system. So in this case, operators should not register a tour that is identical or are covered by an existing ROA, unless there are valid operational reasons. And the tour registrations should be periodically reviewed and updated to reflect current operational practices. And in section 8, we summarize the results of current discussions. The first discussion is about whether it would be feasible to create a special rule for an AS that is not authorized to originate routes to a given prefix as an alternative to implement tour. And we authors consulted ASN1 experts to this approach, and they strongly advised against it because it would extend ROA semantic. And so we also asked other participants in SADROPS. They also recommended against overloading ROA semantics. So the current decision is, we believe defining a new tour object is more appropriate. And the second discussion is about creating a conventional ROA for such scenario, even though the AS is not authorized to originate routes to the given prefix. But it may cause semantic conflict or additional risks of forged origin hijacking. So our current design is the choice is totally rests with the prefix holder. And we also notice the draft was referenced by many other solutions in this working group. So we think it can provide useful information.
I think you can leave time for the questions.
Okay, so I just say, I mean, I read this draft and I understand this, but I can't understand the scenarios, and I think you should motivate these better scenarios in which there is some risk or some problem in announcing a ROA when you actually only want to originate the traffic. So yeah, in principle, it's not, I mean, you don't authorize them to, I mean, you don't need them to announce the prefix, but is there a real scenario, a real attack scenario? Or what is the motivation where you are concerned? And is there a real operator concern about using the ROAs in such case? And in particular, if you think there is such a case, I would recommend that you make this feedback to the BARSAV authors, because then BARSAV should be changed, right? Okay, and I think motivation should be strong, because having there is a big price to having such a separate mechanism. So if there is motivation, make it very clear. If there isn't, then maybe just people should just use ROAs. That's my point.
Yeah, thanks.
Thank you.
Igor.
Yeah. So first of all, just to respond to Amir, Barsev authors are very aware of TOR, and I mean, we will be happy to include it once it becomes actual, like at least an adopted draft. But yeah, I think like you said during your presentation, it really is easy to adopt Barsev to use TOR as a signal as well. As far as concerns why raw could possibly be a threat, need to think through it carefully. But I mean, I can imagine cases when somebody, an attacker, publishes or advertises a route as if it came from the AS that announced raw, that has a raw, and somehow like in a way to attract the traffic to the ASS provider or something like that. Or maybe just in an attempt to maybe overwhelm the OS. Maybe the traffic is quite large and the AS has pretty small links. That could be just a part of an attack on the AS itself, like if it were starting to attract a lot of traffic that it didn't mean to attract.
Yeah, and I would also okay, thanks, Igor. I would also see that there is an open discussion section in this document, but due to time limit, so I encourage everyone to follow the open discussion on the mailing list. Thanks.
Help you with that.
Thank you. Hi everyone, I'm Jing Zhao from China Unicom. Today I will, on behalf of my team, to introduce the draft advertisement of melt source style rules using BGP link state. And we resolved some comments in IETF 122. The first is about how to distribute server rules, and the second is the BGPOS operational procedures. And we update have been made in the draft version there too in response to about these comments. In section 3, we update the BGPOS attribute for cell mode. I just noted the name of the mode is updating, so we will make the corresponding update about it. And in section 4, we added the BGPOS attribute for cell actions. Cell action in this draft adopt the traffic filtering actions defined in RFC 8955 and 8956. And in section 5, we gave some examples of validation modes and cell rules NLL configurations. And in section 6, we added the procedures, the process of reporting cell rules via BGP-LS. The routers running cell mechanism establish BGP-LS settings with the controller responsively to report melt-sourced cell rules, and the routers mainly be the boundary routers or the access routers. And the step 1 is R1 and R2 run cell mechanism and generate melt source cell rules. And the section 2 is R1 and R2 respectively establish cell BGP-LS settings with the controller. And the section step 3 is R1 and R2 generate BGP-LS advertisement for the cell rule NLLs. And the section step 4 is R1 and R2 report melt source cell rules to the controller through the cell rule NLLs. And more comment and discussion welcome. Thank you.
No comments? Oh, yes.
Just very quick question that because this kind of draft you also introduced in IDR work group,
Yeah.
right? So what's the background we, between that we came here to discuss SAVNET work group? What's initial? I mean,
in SAVNET, we just to make sure that the scenario is meaningful, so we can try to use this BGPS to advertisement.
Okay, yeah.
Okay, thank you.
Peter Pshanak from Cisco. So, yeah, this needs to go to IDR. I personally don't believe BGPLS is the right mechanism. This belongs to management plane. BGPLS is not a management plane. So, just a comment.
Thank you.
Hello, can you hear me?
Yes, we can.
Okay, thank you. Thanks to the chairs for hosting this, and let me present our work in SAVNET working group. My name is Cao Qian from Zhongguancun Lab. Today I'll talk about self-information export in IPFix. So as we all know, SAV is a critical mechanism against IP spoofing. But currently it's a black box to operators and security teams. We cannot answer critical questions such as how many spoofed packets we are dropping or which specific sub-rule are triggering this dropping action. Without this data, we cannot prove SAVNets is effective, or we cannot troubleshooting misconfigurations or justify the deployment. So our goal here is to use IPFix to bring this process to clarity. So why do we choose IPFix? IPFix is about streaming data plan events in real time. First, it's a standard and vendor neutral protocol. And secondly, it can carry the structured data for sub rules. And finally, it leverages in existing ecosystems of tools, reducing the operation cost. So it's a perfect fit for sub event information exporting. The approach is to extend IPFix with sub-specific information element. So these elements capture the concept, context, and outcome of every self-enforcement decision. The solution is built directly on top of the sub-architecture. It is conceptual aligned with the general self-capability and semantically correlated to the sub-Young model. So we also utilize the 4 sub-validation modes here. Our elements directly map to these 4 canonical validation nodes that is defined by the SAVNET architecture. So there are 4 nodes, 4 modes. The first 2 are interface-based, and the other 2 is prefix-based. And for both the 2 modes, there are 2 types of sub-rule lists, allow list or block list. And so to encode these 4 modes along with other context of sub-event, we need a set of information elements to capture the whole context. So this leads us to the four new elements that we propose. The first one is sub-rule type. It identifies the rule as an allow list or block list. The second one is sub-target type. It specifies if the rule is interface-based or prefix-based. And the third one is the most important one. It is sub-matched content list. It uses the sub-template list structure to carry the actual content of the rules that we actually evaluated. And the fourth element is sub-policy action. It reports the action applied to the spoofed packets. So these IEs work together to provide a detailed context, including the what and how, and also explains the why. The key design here is sub-matched content list. It captures the specific sub-rules that trigger the decision. Here is an example of a data record on the right side of the slide. It represents an IPv4 allow list non-match event. So in this scenario, a spoofed packet arrived on the interface 5001. It was checked against an allow list, and it didn't match any of the permitted rules. So how does the telemetry explain this? So we use a new IE we proposed here, sub-match the content list. Inside the list, we see two sub-records. Each record represents a sub-rule from the allow list. So the full information of sub-rules are recorded, indicating that the spoofed packet matched none of them. So let's look inside the container to see how the sub-rules are packed inside the list. Each entry of the list is a complete sub-rule, and the rule data is structured using a sub-template. To describe the sub-rules from 4 validation modes, we define 4 dedicated sub-templates for sub-match the content list element. So these templates cover all the combination of address families and validation modes. So the value of these IP-fixed data model is clear in these operational scenarios. Operators can use the data to monitor sub-effectiveness in real time. They can perform root cause analysis to see exactly which rule blocked a packet or a flow. And more importantly, these records related to each other or relate to other data source to help with the incident and threat analysis. So it allows the validation events produced by the sub mechanism to be consumed by external systems. And the operational considerations are simple. For implementation, the main considerations are to encode and decode the sub-template list to ensure the collectors can understand it. And moreover, separate and dedicated sub-templates should be utilized to accommodate different IPv4 and 6 addresses families. Due to the time limits, I'm going to skip the example part. So you can the full context in the draft.
If I may, one quick question just before you conclude. This is Joel Halpern with Erickson, a co-chair of the group, but speaking as a participant, not as a chair.
Okay.
Looking at your encoding, you seem to be reporting with the packet both the rule ID and a bunch of details about the rule. Is it an interface rule? And what action did the rule specify? If you assume that there's some other mechanism to get the set of rules, because IPFix is not about exporting configuration, wouldn't it be simpler to just export the rule ID and not the rest of the information?
Okay, that's a very good question. And we have thought about designing an ID instead of exporting the whole context of the rule. First of all, we do not have a mechanism to assign an ID to every rule. So that adds manual efforts to the operators. So instead, we just want to show the full context, including the content of the triggered rule in real time for the operators or the security teams. So here's the thoughts that we designed this list. And IPFix provide a very flexible mechanism for us to export the data using a structured data data type. I hope this explains the why. Thank you.
Hello, Chair. Can you hear me?
Yeah, you can begin.
Hi. Yeah. Hi, everyone. I present this topic on behalf of the others. This topic is about the young model for SAVNET. We have presented this topic at previous meeting. First, let's review this structure of SAVNET Young. This SAVNET Young model has three paths, namely SAVNET configuration, SAVNET state, and SAVNET events. This Young model consists of three data modules, namely IETF sub, IETF IPv4 sub rule, and IETF IPv6 sub rule. This module structure is similar to the Young data model for routing management. This Young model provides a base framework to configure and manage and subsystem. This Young model, including sub basic configuration and state, and sub table and sub rules. It also specifies the data mode for static sub rules application. And also this Young is designed by referring to the SAVNET general functions. Okay, the SAVNET Young model focuses exclusively on general sub capabilities, and this does not involve dynamic sub rules generation through control plan protocols. We have updated this this draft multiple times based on practical test result and relevant IETF drafts. So we need request more review, and we want request the WG to adopt this draft. Okay, thank you.
Joel Halpern speaking as co-chair. Well, I've looked at this draft and it looks like a reasonable approach. Personally, I don't know why it's echoing. I think it's too early to adopt a Yang draft for this. We're focusing on the problem statements.
Yeah.
Yeah, let's oh yeah, let's
okay.
Probably going from his side.
Oh.
is it-
To mute himself.
so you can mute yourself. Hello? Yeah.
Oh, yeah.
Let's repeat Joel's suggestion. You know, currently we are discussing mainly for the intra-domain and PS document and this architecture. So currently it may be premature to adopt the Yang release document.
Yeah. We thought because this draft is about the basically configuration of SAVNET Yang, and it just involves the sub generation capabilities. So we want the WG to adopt this. Okay. Okay, thank you.
Okay. Hello, everyone. Li Bin Liu from Zhongguancun Lab. On behalf of my co-authors, I present the updates on the benchmarking methodology for intra-domain and inter-domain SAV. This document mainly defines the methodologies for benchmarking the intra-domain and inter-domain SAV mechanisms, which includes existing and the ongoing mechanisms in SAVNET work group. Here is a summary of the historical versions. We have updated 9 versions in total. And after the IETF 1, 2, 3 meetings, we have received many comments from SAVNET and the BMWJ mailing list. So based on this feedback and comments, we have updated 3 versions. For this meeting, I will present the version 08. This is the overview of this document. In this document, we mainly defines 7 self-performance indicators, including the false positive rate, false negative rate, protocol convergence time, protocol message processing throughput. The false positive and false negative rate mainly used to measure the cell accuracy, and the protocol convergence time and the protocol message processing throughput are used to evaluate the control plane performance. And the data plane cell table refreshing rate, data plane forwarding rate, they both are used to evaluate the cell data plane performance. And the last one is resource utilization. So we also designed some benchmarking scenarios to evaluate the intra-domain and the inter-domain cell And also we define the reporting format for the benchmarking results. So we have summarized the comments from the mailing list and our corresponding response. The first type of comment is about the test setup using spoofed traffic with different types of source addresses. Comment from Nangang. The setting of the forged source addresses may have an impact on the test results. An invalid packet may forge an unused source address, private network source address, internal source address, or external source address. So different sound mechanisms vary in their ability to block packets with forged source addresses of various types. We agree with this. So in sections 5.1.1 and 5.2.1, we have added a test setup which requires that under each scenario, the generated spoof traffic should include different types of the forged source addresses. The second type of comment is about a test setup using different ratios of spoof traffic to legitimate. Comment from Nangang and Xue Yansong. For Figure 5, they query about for Figure 5 how we can understand the ratio of spoofed to legitimate traffic. So in the mailing list, we have explained that the ratio of spoofed to legitimate traffic indicates the proportion of spoof and the legitimate traffic among the overall testing traffic. We use this because the proportions of spoof traffic may vary in practice. So we try to simulate the possible rules of spoof traffic in the practical scenarios. Also, we have revised all the corresponding parts in the document and make the tester to generate varying ratios of spoof traffic. The third type of comments is about some performance indicators. Nangang commented that the proportion of the decrease in the data plane forwarding rate would be more appropriate. In our response in section 4.6, we have clarified the definition of data plane forwarding rate and added a suggestion to measure the data forwarding rate with enabling and disabling SAO. Also, Yuan Renzhang commented that some additional KPIs is also useful. For example, the stability or time and the sensibility to table size. Actually, in section 4, we have added the considerations to analyze the standard deviation of KPIs and measure the SAO table refreshing rate and the data plane forwarding rate with varying SAO table size. So the fourth type of comment is about the testing control plane performance. The comment is that not all sound mechanisms actually have a dedicated control plane protocol. So it is better to make it optional. Yes, in sections 5.1 and 0.2 and 5.2.2, we have added the explanations that the tests for control plane performance are optional for intra-domain and inter-domain SAO. The fifth type of comment is on the figures and corresponding descriptions. We have updated the descriptions to about these figures to do the clarification, and also not only about the figures in the comments, we also revise other similar parts in the document. And the sixth comment is about clarifying some terminologies, mainly the definitions of the host-facing and customer-facing router. We have revised these definitions and make them consistent with the definitions in the intra-domain problem statement document. And the seventh type of comment is about adding more real-world testing scenarios, including the FR and the policy-based routing scenarios. And in the document, we have in sections 5.1 and 5.2, we have added 4 new scenarios including the intra-domain, the inter-domain SAV under the FR and the policy-based routing scenarios. And the last comment is about a partial deployment. In fact, in the document, all the benchmarking scenarios are partial deployment. So also a quick summary of the main updates. We have mainly updated the terminologies, some performance indicators, and the test scenarios for the intra-domain and the inter-domain SAV mechanisms. Okay, in the BMWG work group, we have recourse to the work group adoption, and also we welcome the comments from SAVNET work group. Thank you.
Hello, Ron Bonica, HPE, speaking with no hats, individual contributor. First, because we aren't quite sure what the SAV mechanisms will be when they're finally standardized, it might be a little premature to be talking about benchmarking them. But we know for sure that SAV mechanisms will rely heavily upon ACLs, access control lists. I don't know that anyone has ever benchmarked access control lists. Are you aware if that's happened at all?
For this question, there are ongoing work to use a control plane protocol to exchange the SAV-specific information.
It might be interesting. Oh, that's outside. It
No,
might be interesting to see if there are any benchmarks for access control lists as they exist today, because we know that will be part of the SAV mechanism.
Okay. I want to answer the first question. This is a general benchmarking mechanism for the SAV mechanism. So, for the SAV mechanism, it includes existing ones such as URBF-based mechanism.
Mhm.
So not only including the new ones. Yes.
Okay.
Okay. Thank you.
Out of the queue. It appears that we've reached to the end of the agenda. Should we talk about next steps for the working groups? Okay, not yet. Okay. Well, thank you all very much, and we'll see you in Shenzhen. Shenzhen. Kill the mic? How do you do that? Oh.
And those mics pick up the music.
Yeah. Are there actually any benchmarks for ACLs? I don't think there are. And they're very expensive.
Yep. Well, that's some implementations they are, and some they're not, and in some, the first one's not expensive, but more of them are. I've run into also